Okay, hello students. What we're going to do now are the practice exercises for Chapter 3, Section 2. This is on page 233 of your textbook. And you are asked to identify the main connective in the following statements by circling or highlighting it. So what we're going to do is take a number of expressions and then we're going to circle or highlight the main connective, and what I'll do up on the board here is to circle it in red. But if you highlight, or if you're taking the test online or electronically, any way that you have of indicating the connective will be proper. Let's take a look at number 1, A and not B. Now the main connective here is the dot. Notice it's next to the tilde, and this is the only time that two connectives can be next to each other. If there's a connective and then it's followed by a tilde, and that's because the tilde is negating what follows it and is functioning together as a unit like a negative number in mathematics. Let's take a look at 3. What do you think the main connective is in number 3? Here we have L or M and N. The main connective here is the wedge, correct? Because the left disjunct is simply the letter L, and the right disjunct is the parenthetical formula M dot N. It's grouped together, so it's functioning as a unit. So we've got this unit connected by the wedge to this unit. Notice here right away a very important observation. The main connective will never, ever, ever be inside of a set of parentheses, brackets, or braces. The main connective will always be on the outside. And here there's only one possibility. Your eyes can go directly there. It's the only connective outside of a set of fences. Let's try number 5. Here we have, it's not the case that A implies L. Now, following up on what I just said, the only connective here outside of the set of fences is the tilde. It's the main connective. So remember that by our formation rules, a tilde is the main connective if and only if it negates absolutely everything that follows it. Here, the range of the tilde goes all the way across the A and the L. It negates everything in the rest of the expression. Try 7. Not A implies C. What's the main connective there? Right. It's the horseshoe. Why? It can't be the tilde because the tilde ranges only over the A and then stops. The tilde does not negate everything that comes after it. Not A is operating as a unit, the antecedent. The horseshoe is connecting the antecedent, not A, to the consequent C. Okay, let's go into taller grass, if I can put it that way. In number 9, now we have either it's not the case that X implies A or both M and B. What's the main connective? This one's a little bit harder, but I think you can solve it. What's the main connective? The main connective is the wedge. Why? Notice that the tilde ranges only over this set of parentheses and stops right there, so the tilde can't be it. And everything else is captured together by fences. So it's the wedge that connects this negated set of parens to this set of parens. It's the main connective. 11 has an important moral principle to it as well. Notice that it says, if G, then both H and not I, if and only if P. What's the main connective here? Right. It's the triple bar. Why? Because this set of brackets groups together all of this in the left equivalent. The right equivalent is simply P. So it's the triple bar. Notice again, the triple bar is the only connective outside of a set of fences. So it's got to be the triple bar. The important principle here is that the main connective doesn't have to be flush in the middle of the expression spatially. In other words, the expression can be very lopsided. We've got a lot of symbols over here and just one symbol over here, but that doesn't matter at all. The main connective is still the triple bar. Let's continue on. 13 has a lot more symbols in it, but don't let that intimidate you. Use the same ideas. What would be the main connective of this expression? By our formation rules, we know that it would have to be the first tilde, the first down of three tildes, the tilde on the outside of braces, or brackets rather. Why? Because the brackets group together all of this expression here into one unit. This is all operating as one unit inside of the brackets. The only connective outside of the bracket is the tilde. To refer back to a previous formation rule, we can remember that the tilde is the main connective if and only if it negates everything that comes after it. Well, this tilde negates everything that comes after it. So the first tilde is the main connective. Let's try now number 15. This piggybacks on one of the previous examples. We've got a lot of symbols going on here. What we're told is that Z implies both if not Y, then not W, and not U. What is the main connective? I think you can see it. It's the first horseshoe. Notice that it's the only connective outside of a set of fences. So it's got to be the main connective. Notice as well, looking back up at number 11, you've got another very lopsided expression. Here in the antecedent, you've got one letter, and in the consequent, you've got a rather complex formula. That doesn't matter. The main connective doesn't have to be square in the middle of the expression spatially, only from a logical point of view. Now, all of this should help for number 17, even though we add more letters. Don't let that intimidate you whatsoever. Just take it one step at a time. In number 17, we have if either both V and X or not I, then neither L nor X. What's the main connective here? I think you can see again that it's going to be this horseshoe. There's only one horseshoe here. It's going to be the horseshoe. Now, we could say, well, gosh, it's not the only connective outside of a set of fences because you've got the tilde here. But remember that a tilde is always going to negate what comes after it. So this is operating as a unit. And this is operating as a unit. It is a well-formed formula. It is well-formed, but that's because this tilde isn't competing with the horseshoe. It's just operating as a unit to negate L or X. Okay, we're almost done with these exercises. You can see it's really rather simple. All you're going to have to do is to just highlight or circle a connective. We've only got one more in this set of exercises. So we're going to go over to 19. It's really quite complex. But again, what we want to do is to not let that intimidate us and to simply take it one step at a time and think logically and apply the same rules that we always have. Looking at this guy, what we have here is not both A or B and R or O unless K implies L. Well, what in the heck is the main connective? Well, we can look at this and see that the tilde ranges only to the closed bracket, and then it has no more effect. This expression over here is captured by fences, the set of parens. And so the main connective here is going to be the wedge way over here. It's connecting the negated brackets to the parenthetical remark. Okay? Now, when I do this live, I always, for the last 41 years, have always had people raise their hand at this point and say, Mr. Whitlock, what about number 18? That's an odd-numbered one, but let's take a look real quickly at that, and I'm not going to answer it. But I am going to give you the basic question you have to ask to answer it for yourself. Here's the expression. It's not false that either L and P or not B. What's the main connective? I'm not going to tell you, even though I already have in a sense in between the lines by saying that the main connective is always going to be the last connective that we solve for. What would be the last connective we would solve for? If we put in values for L and P and B, we'd get the values of the dot, then the tilde, then the wedge. Then we'd come here and get the value of the second tilde, and only then could you get the value of the first tilde. Okay, so that completes the exercises on identifying the main connective. That was Roman numeral number 1. Now what I want to do is to go to Roman numeral 2 on page 234, and we're going to do the odd numbered ones to number 23. So 1 through 23. And in these problems, we're going to let A, B, and C all be true statements, and we're going to say that X, Y, and Z are all false statements. And we're going to ask, determine the truth values of the following statements. So what we're going to do now is not only similar to algebra, it is the same as algebra because we're doing a kind of Boolean algebra, but applied to propositions rather than to numerical values. So let's take a look at this guy. The way that you do it is to plug in what you know and to solve for the main connective. Oh my gosh, the main connective, that's what you just learned to identify. We're piggybacking on the skill that we just learned, identifying the main connective. Taking a look at this one, what we know is that Z is false. We were given that in the instructions. X, Y, and Z are false. So we know that Z is false. If Z is false, then not Z must be true. So we put a T under the tilde. It's the main connective. So we circle the T, we're done, that's the answer. Now in all these problems, I'm going to ask you to highlight or circle your final answer, and that would be this. Showing your work would be plugging in truth value for the letters. And what I'm going to do is to draw arrows, but you don't have to get a correct answer. The arrows are going to answer the question that I'm always posed. Where did you get that value? The arrows show where I got the value from. So the arrows are going to be crucial, but you don't need in your correct answer to put them. Okay, now let's go to number 3. Here we have A dot, not Z. How do we solve this? Again, it is the same process no matter how gigantic the formula or how teeny tiny the formula. You plug in what you know, you solve for what you don't know. The last thing that you solve for is the main connective. Here we know that A is true, so we'll put a T under the A. We know that Z is false, so we'll put an F under the Z. Now we need to solve for this tilde. If Z is false, not Z will be true. Now we solve for the dot, that's the main connective. So we know our answer is going to be right under the dot, so we can draw a circle under the dot. Here's where my answer is coming. True, dot true, makes the dot true. So my final answer is true. The connectives always, always, always operate in the same way. You take the left side as a whole and the right side as a whole, and then your knowledge of the main connective. Here the left side as a whole was true. The right side as a whole was true. You got a dot between true and true. When both sides of the dot are true, the dot is true. That's what the truth tables are telling you in terms of the truth functional meaning of the connectives in the text 3.2. We're just applying those truth tables here now. And when you do dozens and dozens of these problems, the meaning of the connectives will just come quicker and quicker to you. Let's try number 5. Here we have not C or X. Okay, we're going to apply the same principle. We're going to plug in what we know, solve for what we don't know. The last thing that we'll solve for is the main connective. Here we know that C is true, so I'll put a T under C. And if C is true, then not C has to be false. Over here we know that X is false, and the main connective is the wedge. So my answer is going to appear under the wedge. One thing you can do that is helpful is to draw a big circle under the main connective. Here's where my answer is coming. Then I take the left side as a whole, it's false. And the right side as a whole, it's false. And I use my knowledge of the wedge. When both sides of the wedge are false, the wedge itself becomes false. So the final answer here is false. Let's go over to number 7 on page 235. Here we have Z implies not B. Well, what do we know? We know that Z is false, so I put an F under the Z. We know that B is true, so I'll put a T under the B. But look, if B is true, not B has to be false. Then we get the value of the horseshoe. So I'm going to put a circle under the horseshoe. That's where my answer is going to appear. Now, What this does is to require you to know the truth functional definition of the horseshoe. That's the hardest of the connectives. False, horseshoe, false makes the horseshoe true. So this horseshoe is true. The horseshoe is the hardest connective to figure out. Its truth functional definition is that the horseshoe is always true unless the left side, the antecedent, is true and the consequent false. But here the antecedent is false, so that's automatically going to make the horseshoe to be true. Put a star next to number 9. This is going to be important for you to understand. It's what you could call a building block problem. The principle here is going to come up again and again all the way to the final exam, so it's important. What we've got here is not both C and not X. What you always do is start inside of a set of fences and work out. Start inside of fences and work out. So what we're going to do is we're going to go inside of the set of fences here. I'm going to rewrite this problem down here, again, without changing it. We're going to go inside of the set of fences, inside of the parentheses, and we're going to plug in what we know. We know that C is true, so I put a T under it. We know that X is false, so I put an F under it. But look, if X is false, then not X has got to be true, right? Then we solve for the dot. So I take the value of the left side as a whole, which is true, the value of the right side as a whole, which is true. True dot true makes the dot true. The only time a dot is true is when both sides are true. Or as I put it informally all the time, the dot is picky. It's very picky. It demands both of its conjuncts, both sides of it, be true to be true. Okay, so now I know that everything inside of the parentheses is true. To get the tilde on the outside, I reverse the value of the governing connective inside. The governing connective inside is the dot. It's true, so this tilde is false. This is the principle that's going to come up again and again and again 100 times. The tilde on the outside of a set of fences reverses the value of the governing connective inside. To put it another way, this tilde is not negating the C. This tilde is negating the value of the dot. Let's try another one and introduce the triple bar into this set of exercises. In number 11, we have Y, if and only if, not C. Okay, now what we know here from the instructions is that Y is false. So we put an F under it. We know that C is true, so we'll put a T under it. But if C is true, isn't it obvious that not C is going to be false? So now to get the value of the main connective, the triple bar, I take the left side as a whole, which is false, and the right side as a whole, which is false, and my knowledge of the triple bar. Remember that the triple bar functions in every way like an equal sign in math. Okay, it's true when both sides have the same value. So here we've got false, triple bar, false. Those are the same value. So here the triple bar is true. Now, you might pause for a second here and say, well, gosh, how do I know the values of these connectives? That was the point of the material in 3.2. You have to understand the meaning of the connectives and not by memorizing T's and F's. Don't try that. Instead, understand what each of the connectives means. This connective if and only if, the triple bar, means basically they're the same, they're equal. It's an equivalent sign. Equa, same, valent, value. Equivalent, they have the same value. Here they do have the same value. So it's true. Going to 13 at the top of page 236. Only a little bit more complicated. There's a set of parens, and we've got 3 letters. But we solve it in precisely the same procedure. Plug in what you know, solve for what you don't know, which will be the connectives. The last thing that you'll solve for is the main connective, and that's the answer to the problem. Looking here, we know that A is true, so I put a T under it. We know that Z is false, so I put an F under it. We know that this B over here is true, so I could go over and put a T under it. Now go over here inside of the parens and work out. Always go inside and work out. True dot false will make that dot false. Why? Remember, the dot is picky. It demands both sides have got to be true for the dot to be true. That's what the truth table in 3.2 had shown us. So this dot is false. I've got the right side over here already, so I solve for the main connective. The main connective is the wedge. So I'm going to take the left side as a whole, which is represented by the governing connective, the dot. It's false. And the right side as a whole, which is true. So now I've got false, wedge, true. That makes the wedge true. Why? Because the wedge is not picky. If at least one side is true, then it's true. And I say at least one because if both sides were true, the wedge would still be true. Okay, so you should think of the wedge as saying at least one of these statements is true. False, wedge, true would make the statement true as a whole. Now, some of you will absolutely hate this method of having all the truth values on the same level. Some people just simply can't do that. So they do a drop-down method, which is perfectly legitimate. I'm going to show you what that would look like by putting this problem up again. How you would use the drop-down method would be, again, you would put the values of the letters in like that. But now for the value of this dot, you drop it down. Drop it down here. There's the F. Drop this down here. Again, it's true. So to get the value of the main connective down here, then you take these two values, make it true. If that helps, do it. I'll understand what you mean. Some people as well like to make a little tree diagram out of it by adding branches like that. That's okay too. Do what you need to do to keep yourself straight on these. Okay, looking at 15, that looks kind of funny, but some people, for whatever reason, may be intimidated by triple bars. So number 15 is designed to completely defuse any worry that you've got about triple bar and to show that it's really probably the most user-friendly out of all of the symbols. Here what we've got is B if and only if A is a necessary and sufficient condition for Z if and only if Y. How are we going to do this? Well, with the longer expressions, Sometimes it's helpful or even necessary to say, I'm going to identify the main connective first. It's this guy. So here's where my answer is going to occur. And put a big circle under where your answer is going to occur. Then put in what you know. Here you know B is true and A is true. Put in T's under them. You know that Z is false and Y is false. Put in F's under them. Now you go inside of the fences and work out. Here you got two sets. It doesn't matter which you start with. True, triple bar true, would make this triple bar true because they have the same value on both sides. True equals true. That's a true statement. So that triple bar is true. Now look over here. False, triple bar false. They are the same. So that makes this triple bar true. Okay, and to get the answer for the main connective here, I take the left side as a whole, which is true, and the right side as a whole, which is true. True, triple bar true, same values, they're equivalent. That means that the main connective is true. Boom. 17 adds more characters, but don't let that intimidate you. This method especially shows you can only do this one step at a time. If you do it one step, little step at a time, you'll get the right answer. Here what we've got is either both both B and X, or both not Y and A. What we want to do here is we can identify the main connective, that's the wedge, so my answer is going to occur under the wedge. I know that B is true, so I put a T under it. I know that X is false, put an F under it. Over here, I know that the Y is false, put an F under it. I know the A is true, put a T under it. Then I apply the same principle of going inside of the fences and working out. So I've got true dot false. That makes that dot false. Because again, the dot's picky. And not both of them are true. So the dot becomes false. Going over here now, it would be easy to make a mistake by just ignoring this tilde. But you have to get a value for the tilde. If Y is false, not Y has got to be true. So now for this dot here, we've got true dot true. That's going to make that dot true. In order to get the value of the main connective, I'm going to take the left side as a whole, which is false. The right side as a whole, which is true. Okay, now I'm challenged again. Do I really know the meaning of the wedge? The wedge is true when at least one side of it, at least one disjunct, is true. Here I've got false, wedge, true. At least one side of it is true. At least one disjunct is true. So that wedge is going to be true. The nice thing about this technique is no matter how long these expressions get, the process never changes. If you know the process on the easiest ones, you can simply apply them to the harder ones and you do fine. And they really don't get very much harder. We're approaching the hardest ones now. Take a look at this guy, number 19. Not B unless X implies C. Okay, what's the main connective here? The main connective is going to be the wedge, so my answer is going to appear under the wedge. I plug in what I know, which is that B is true, X is false, and C is true. Then I go inside of the parens and work out. False, horseshoe, true, makes the horseshoe true. The horseshoe is the one that you're going to learn last. It is counterintuitive, but when you have false, horseshoe, true, the horseshoe is true. The horseshoe is always true unless the antecedent is true and the consequent false. Now going over here, this is real easy. If B is true, then surely not B has got to be false. To get the value of the wedge as the main connective, then I take the value of the left side as a whole, false, and the value of the right side as a whole, which is true. So I've got false, wedge, true, at least one disjunct is true, so that wedge is true. If you understand the basic procedure in the easy problems, the harder ones just take longer, but they're in principle no more difficult. Let's take a look at 21 as an example because it's got a lot of symbols to it. Both A and, it's not the case that either not X or not both B and not Z. There's a lot of stuff going on there, but we take it one step at a time. What we're going to do here, and here I think especially, you can see it would be helpful to identify the main connective so I don't get lost later. The main connective here is the dot, so my answer is going to appear right there under the dot. Now, A is true, so I'll put a T under it. X is false, so I put an F under it. This B is true, so I put a true T under it. And the Z is false, so I'll put an F under it. Good. But oh my gosh, how do I proceed? The same principle. Start on the inside and work out. If you've got two sets of fences, like here, the parentheses and the brackets, go to the innermost set of fences. So we go to the innermost part of the expression right here. Look, if Z is false, then not Z has to be true. And if you've got true dot true, that's going to make that dot true. Then to get the value of this tilde here, which would be easy to forget, this is a little glitch here, it'd be easy to forget this tilde. The tilde is going to reverse the value of the dot. So the dot was true, that means the tilde is going to be false. I know that the X is false, but since X is false, that means not X is going to be true, so that tilde is going to be true. Then I use the left disjunct as a whole, which is true, and the right disjunct as a whole, which is false, and the wedge. True, wedge, false would make that wedge true. But I've got a tilde out here that also is going to be easy to overlook. It reverses the value of what? Right, the wedge. So I'm going to reverse the value of the wedge, which is true, to get that tilde to be false. Now you can see the reasoning why some people absolutely hate having all the T's and F's there. Isn't that kind of confusing? Yes, it is. One thing that I do to keep myself straight in a live session of this when I'm up at the board and possibly making mistakes is when I get one side of the main connective done, I put the value in a box. That would mean this value could go in a box. This value goes in the box. So that what that means is at the very end, these are the only letters I'm focusing on. So now I get the value of the main connective, the dot, by getting true from the left, false from the right. True dot false makes that dot false. Because it's picky, it demands both of its conjuncts or sides be true for it to be true. So the final answer is that the main connective, the dot, is false. If you want to come up with a system of laying these out so that it makes sense to you, I should be able to figure out what you're doing. Again, you don't have to do any of these arrows. That's to answer your question, where in the heck did you get that value from? The arrows show you where I got the value from. You do not have to use them if you don't want to. Let's try 23 here. This looks like a formula for rocket fuel, and I add this only to drive home the point that you're going to use the same process again and again, so don't let a complicated formula intimidate you. Here we've got a rather complex formula. It would read something like, if both A and B then not Y is a necessary and sufficient condition for not both A and B unless not Y. What's the main connective? After going through all this, you see you're reinforcing those earlier skills. What's the main connective? Now it should be super easy. Oh my gosh, the main connective is that triple bar in the middle. My answer is going to appear there. Every one of my problems is going to reinforce previous skills. Now, I go and fill in what I know. I know that the A is true, B is true, this Y over here is false, the A here is true, the B here is true, the Y way over here is false. Now I go to the innermost set of fences and work outward. There's two set of innermost fences. It doesn't matter. Let's go here. True dot true will make the dot true. And here I'll drop them down a little bit because on the board it is kind of cramped. I'll drop these down a little bit. That dot's true. Well, over here now, if Y is false, that means that the tilde will be true. Okay. To get the horseshoe here, I'd have true, horseshoe true, that will make the horseshoe true. So everything on this side of the main connective is true. Now let's go over to the right side. Again, we want to start inside of the parens and work out. This one's got a little glitch. Inside is true dot true. I hope that's clear at this point that that does satisfy the picky dot and make that true. But notice here this tilde would be easy to space out. The tilde here is going to reverse the value of the dot that we just got, which was true, so this tilde is going to be false. Now we go over here, the Y is false, so the tilde in front of it will turn out to be true. Now we've got this wedge. The left side of it is false, the right side is true, at least one side is true, so that wedge is true. And the wedge represents the right side or the right equivalent of the expression as a whole. So at this stage then what we see is we've got true, triple bar, true. Again, I'm using these boxes just to make it super clear visually where I'm at. True, triple bar, true. We'll make the triple bar true, boom, I'm done. I didn't do anything different than the simplest exercises, I just did it more often. That was number 23 on page 237. And I'll tell you at this point that that is the gold standard. So if you can do number 23 on page 237, you're set to go. You'll do great. That's as difficult as I'm going to expect. Although, again, numbers 24 through 31, if you want to do those as practice, more power to you. The harder ones that you master, the easier the earlier ones are going to be. So if you work further, that's just fantastic. The last set of exercises for 3.2 occurs on pages 239 and following. What we're going to do, again, as usual, are just simply the odd-numbered ones. And then at home, you can do the even-numbered ones and check yourself against the answer key. On these, practice makes perfect. The more you do, the more confident you feel. So just try and do as many as possible and check yourself against the answer key. Now, in those exercises we just did, we knew all the values. A, B, and C were true. X, Y, and Z was false. Now we're going to add a little complication, and one of the letters, we're not going to know the value of it. So in Roman numeral 3, beginning on page 239, what we're told is that A and B are going to be true statements. Y and Z will be false statements, and P and Q have an unknown truth value. We don't know whether they're true or false, but we want to see if we can determine the truth value of a longer expression that has a letter with an unknown value. Maybe we will be able to determine it, maybe we won't. What this process does here, this skill, is to really reinforce our notion of deduction. Remember that deduction is that property of any argument such that the conclusion is 100% certain given the truth of the premises. In order to be able to arrive at a conclusion with 100% certainty, we have to cover all of the possibilities. So when we don't know one of the letters, like Q in number 1, what we'll do is we'll cover all of the possibilities. We'll cover all of the bases, so to speak. So what we're going to do here is we are going to create a little truth table. And under Q, since we don't know what it is, we'll cover all the possibilities. We don't know what Q is, but by our realist assumption, it's got to be either true or false. We're going to cover all the bases. We're going to hedge our bets, as you might say as well. But we know that A is true, so on both lines, we're going to keep A true. So A is always true, and then we cover all the possibilities for Q. The answer then is going to be deductive in nature. Now what we do is to solve for the main connective, the wedge, on each row, taking one row at a time. So again, this is going to be hundreds and hundreds of opportunities to practice your connectives. On the first row, true, wedge, true makes the wedge true. So I put a T there. And on the second row, true, wedge, false would still make the wedge true because at least one disjunct is true, at least one, so it's true. The wedge is not picky. Okay, now what do we do? In order to arrive at the answer, we read or interpret the truth table. And we do that by looking entirely down the column that represents the main connective. The main connective here is the wedge, so this is the column we're looking at. We're looking now only at these two values. Both of them are true, so what that means is that this expression is true, and I'm going to ask you to not only circle that main connective column, I'm going to require you to write it out to the side to make it super clear. Even though we don't know what Q is, the expression A wedge Q is always true. Let's try that with the dot. Going to number 3 is B dot P. Now, we're going to create a little truth table under it. We don't know what P is, but again, by our realist assumption, we know that that P is either going to be true or it's going to be false. So we're going to cover all of the bases, all of the possibilities, making it a deductive process by having one row where P is true and one row where P is false. We know as a given fact that B is true, so we'll put T under B on both of the rows, all of the rows. Then what we do is to solve for the dot, the main connective, one row at a time. And on the first row, true dot true makes that dot true, so we put a T there. But on the second row, true dot false makes the dot false. Because it's picky, it demands both sides of it be true, but one side's false. So on the second row, the dot is false. Now, to get my answer after I've completed the truth table, I interpret or read it by looking at the main connective column under the dot. And I see that the dot is sometimes true, sometimes false. In other words, I cannot determine the truth value of the expression B dot P. So I put a question mark. That's my answer. I can also write out unknown or indeterminate. Any of those three are allowed, but I think by human nature, you're probably going to go easiest and just do the question mark. Okay, so you'd put a question mark out here. Remember, this is super important. Question marks never ever go inside of a truth table. The question mark is the final answer. It's never going to be inside of a truth table. Let's try another number 5. This is the last one on page 239. Here we have if B, then P. Going to solve this the same way. We're going to write a little truth table here. We don't know what P is, so we'll cover all of our bases or hedge our bets and have one row where it's true, one row where it's false. And under B, we're told that it's true, so we're never going to change it. It's just going to be true. Then we solve for the main connective. That's the horseshoe. This is going to reinforce our knowledge of the horseshoe, which we always need. On the first row, true, horseshoe, true, makes the horseshoe true. But on the second row, true, horseshoe, false, makes the horseshoe false. The horseshoe is always true unless the antecedent is true and the consequent false. This horseshoe then on the second row would be false. What that means then is that now I am going to look at just these two values for the main connective. And what I see is sometimes the expression is true, sometimes the expression is false. So the value of it is unknown. I cannot determine it, so it's indeterminate. Putting it another way, the value of it is unknown. Any of those three answers, this is what I call the interpretation or the reading. It's the interpretation or reading of the truth table. Let's try a few more here. Let's see, number 7 is a great deal like number 3. We won't worry about it. But let's go to number 9. Here we've got Z triple bar P. This will give us a little practice with our buddy, the triple bar. We're going to create a truth table under it. And as far as that goes, when you're taking this at home electronically in order to make it convenient for you, I am going to have the truth tables set up. The graphs will be set up already for you. So what you would see on a test would be this. And then you'd fill in the truth values. Now, we don't know what the truth value of P is, so we hedge our bets and consider both possibilities. It's either true or false. We know for a given fact that Z is false, so we'll keep it constant at false on all lines. Then we solve for the main connective. I think it's obvious to you by now, it's the triple bar. This again gives us practice at our calculation of truth values for the connectives. On the first row, false triple bar true would be false because they're not the same value, they're not equal. Thinking of it mathematically, they're not equal, so that's false. But look on the second line. False, triple bar false, those are equal. They're the same value, so here the triple bar is true. So, interpreting my work here, I'm looking now just at those two values under the triple bar, and I see that sometimes it's true, sometimes it's false. So the value of the expression as a whole is question mark, or indeterminate, or unknown. I think we should cover number 11, because this is going to reinforce an absolutely crucial process in our logic calculations. Looking at it here, we've got, it's not the case that P implies Y, like so. Now, we'll make a truth table for it, like so. 2 rows, because there are only 2 possible truth values for P. P is either true or it's false. Y we know to be false. So we're going to keep it false on all rows. Then next, we calculate for the horseshoe. We're going inside, working out. Notice you do not take the P values and reverse them to get the tilde values. The tilde is reversing the value of the horseshoe. So we have to get the horseshoe values first. This will give us more practice on the most troublesome connective. True, horseshoe false makes the horseshoe false. It's the only time that the horseshoe is false. On the second row, false, horseshoe false is actually making the horseshoe true. Now and only now can I go over and get the values of the main connective, the tilde. And here's where that crucial principle comes in again. The tilde out here is reversing the value of the governing connective inside of the fences. This tilde is not reversing the value of P. The tilde is reversing the value of the horseshoe. Okay, so if the horseshoe is false on the first row, the tilde is going to be true. And if the horseshoe on the second row is true, the tilde outside is going to be false. Now I've completed my truth table for this expression, and I'm looking only at these 2 cells right here under the main connective. And I read or interpret it to mean that sometimes the expression is true, sometimes the expression is false. It's unknown. We don't know what the truth value of this longer expression is. We're going to skip 13, but let me say that the only typo in the entire textbook is right here. Number 13 should read, it's not the case that B or Q, not B or Y. So number 13 on page 241 should actually read, it's not the case that B or Q rather than Y. That was just like the last one we did, number 11. So what we're going to do is start skipping a little bit more radically through these. Let's go down to 15. Here we have A, if and only if, P dot, not B. This just is going to have more columns in our truth table. It's not going to have more rows. But I think you can see here as well that it might be of some value to identify the main connective and mark it, so you know which column you're ultimately going to be looking at for your answer. Now, in the instructions, we don't know whether P is true or false, so we'll have one row where it's true, one row where it's false. But we know that A is always true, so we're going to keep it true on all rows. And we know that B is true, so we'll keep it true on both rows. Now what we can do is to, again, use our principle of going inside of parentheses and working out. Let's go to the first row inside of the parens. If B is true, surely not B will be false. So that tilde gets an F. Then we solve for the dot. True dot false. We'll make that dot false because not both of the conjuncts are true. It's picky and this one didn't make it, so the dot here is false. Then we go to the value of the main connective, the triple bar. On the left side we've got true, on the right side we've got false. So true, triple bar, false, those don't have the same value. So this triple bar on the first row will be false. Now let's go to the second row and again go inside of the parens and work out. Here again B is true, so again not B would have to be false. And here if we've got false dot false, that for sure is going to make the dot false. So to get the value of the triple bar, we're going to take true, triple bar, false. Those aren't the same, so that triple bar is false. Now, I have filled in the truth table completely. I'm looking only now at the cells under the main connective. And I see that this statement is always false. Even though I don't know the value of P, the formula is always false. So I write out to the side false, and circle or highlight it, and there's my interpretation, and I'm done. We're going to skip 17 because it's similar to 15 and even easier. Let's go to 19. We're almost done with this skill set. We'll do two more kind of quickly, just to reinforce this. We'll add some more characters, but the principle remains the same. Let's try 19. Neither P nor A implies B. Okay. Got a lot more columns. That's no big deal. I'm going to draw the columns down, completely ignoring the fences. They don't matter. And again, we have got P as unknown, so we'll put it true on one row and false on another. We know that A is true, so we'll keep it true. We know that B is true, so we'll have a T for it on both rows. Then we go inside innermost fences, the parens here. True, horseshoe, true, true. And on the second row, again, true horseshoe true makes the horseshoe true. Then we go to the wedge. It's the governing connective inside of the brackets. True wedge true would be true because at least one of them is true. At least one is true. And on the second row, false wedge true. At least one is true, so it's true there. Then to get the value of the tilde on the outside, that's the main connective, we're going to reverse the value of the wedge. This tilde does not reverse the value of P, it reverses the value of the wedge. So on the first row, the tilde will be false, and on the second row, the tilde will be false. That means, looking under the tilde, that this expression is always false. That would be the final answer to write out to the side. Let's do one more in this skill set. Let's try 23. It's kind of a funny one. If P implies P, then P, then P. It's just got one simple statement to it. But it's used 4 times. This might rattle you. It should not. What can we say about the P's? Well, they're going to always have to have the same value going across the row. And we don't know what value it has. So on the first row, we're going to make P true, and on the second row, we'll make P false. And then we'll proceed with that all the way across. So all 4 times under the P, it's going to be true on that first row. And on the second row, the P is going to be false all 4 times. Now let's concentrate on the first row. Go inside of the innermost set of innermost set of fences. True horseshoe true will make that horseshoe true. Then we take that value and this value. True horseshoe true again makes the horseshoe true. We take that value we just got here. True horseshoe true will make the main connective here true. Boom. That was easy. Let's go to the second row though. Inside of the fences, innermost set of fences, the parens, false horseshoe false makes the horseshoe correct, true. Now, true horseshoe false would make this horseshoe false. Then I take that value and the value of the last P to get the value of the main connective. False horseshoe false makes the horseshoe right, true. So to interpret the truth table, I'm looking only at these 2 values under the main connective. They're both true, so this formula is true, even though we don't know the value of P and it's the only letter that occurs. Now, here's an interesting question. Looking at 22, we see it's the same formula, but one set of parentheses is moved over. Does that matter? I'm going to leave that for you at home to work through. Don't make any assumptions. Do the same process for number 22 and see what the truth value of it is. That completes our exercises for 3.2.